We've all seen rounding numbers when we do math using calculators. They are a result of the way that we store real numbers. To see how we do that, let's look at how 16 1/4 would be stored. We use a technique called floating point notation. For the details of that format, check out the video above. But for this discussion, it's enough to know that floating point notation is very similar to scientific notation. Real numbers can be represented as a number times 2 to a power. We use the powers of 2 instead of the powers of 10 because we're storing everything in binary. Just like multiplying by 10 moves the decimal place 1 position in base 10, multiplying by 2 moves the decimal place 1 position in binary. We call the numbers that are parts of the floating point numbers the mantissa and the exponent. Both of these values are fixed length binary numbers. So essentially, we store one real number by storing two integers. That gives you a clue for why rounding errors happen with floating point numbers. Yes, some rounding errors come from the way that we do individual operations, but some come from the fact that the mantissa is a fixed length binary number. That means that the precision we can hold is limited by that length. In other words, the range of the mantissa is bound, just like the range of integers is bound. Imagine in scientific notation that you're only allowed to have 3 decimal places. That doesn't bound the range of values you can store. Remember that exponent could make the resulting number really big or really small. But it does bound the precision that your number can have. Well, if that's the way we're storing things, how do we do math with them? Let's look at multiplication and division first. Multiplying two floating point numbers looks like this. We want to rearrange and do some arithmetic to get to a single mantissa and a single exponent. Let's use commutativity to group like things. Now we can get one mantissa by multiplying those two mantissas, and one exponent by adding the two exponents. Just like with scientific notation, there are rules about where the decimal place has to be in the mantissa, so we might need to shift that by adding or subtracting to the exponent. But we're essentially there. That wasn't too hard. Let's think about one more thing. Remember, that exponent is a fixed length integer. What happens if we overflow it? Look at this code. A double in Java is a 64-bit IEEE 754 floating point value. That means that it has 11 bits for the exponent. That means the biggest positive exponent that it can hold is 1023. Details in that IEEE 754 video. Multiplying that by 2 would make the exponent too big to hold. Let's see what happens. Ooh, unlike integers where overflow resulted in weird behavior, it gives the value infinity, which basically means that it's smart enough to know that the number got too big. IEEE 754 has 3 special values that it can use to tell us that weird things happened. Positive infinity and negative infinity, which means that the exponent got too big to hold, and not a number, which means we did something illegal, like divide by 0. Addition and subtraction are a little harder to follow, so let's do it in decimal first. Suppose that I wanted to add 2 numbers that are written in scientific notation. Remember, we want to end up with one mantissa and one exponent. In order to be able to combine the exponents, the first thing I need to do is make the exponents the same. We do that by shifting one of the mantissas so that it needs to have the same exponent as the other number. Then we can use the distributive law to pull out one exponent. Add the 2 mantissas, and we're there. Now, let's look at what that looks like for 2 floating point numbers. The first thing we have to do is shift one of the mantissas so that the exponents match. Let's assume that the first number is the larger number, so we want to shift the second one to match the first one's exponent. Let x be the difference between the 2 exponents. We know that will be non-negative because we said the first number was larger than the second. So we can use that to get rid of the second exponent. So first, solve for E2, and then substitute that into our addition problem. That's saying that we need to move the decimal point in the second mantissa by x positions to make the exponents match. Once we do that, we can add the mantissas to get the results. That shifting is the thing that we need to be worried about. The effect of that shifting is that we are adding leading zeros to the integer that we're storing as the mantissa. If x is large, we might shift the bits of that number so far that they don't fit into the fixed space we have for the mantissa, which will essentially make the second number 0. To show why that matters, let's look at this piece of code. It's trying to add 1,000 teeny things to one big thing. The first time, it adds all of the little things together, and then adds the big thing. The second time, it starts with the big thing, and then adds all of the little things to that. In math class, addition is commutative, so these things should get the same result. However, when I run it, this is the output. The two results are not the same. And look at this. Largest first has the value of the one big thing. It looks like we didn't add anything to it at all. To explain what happened, remember what we just talked about in adding numbers. In the first addition for largest first, we are adding 1 times 10 to the 16th and 1 to the negative 1021. That's a really big number and a really small number. The shift that we're going to have to do is in binary, but the difference in the binary exponents is going to be huge. As a result, we're going to shift that little value's mantissa right off the end of the fixed length binary number, and that'll make it 0. So the largest first code is essentially adding 0 to the big number 1,000 times. In the smallest first code, we add all those little things to each other, which does not make them 0, so then they can accumulate. When we add the result of all of that to the big number, it's big enough that it doesn't get shifted away in the arithmetic. So addition is not always commutative in the computer. If we're adding things with very different magnitudes, we should add them smallest to largest in the hopes that the little things accumulate enough to not get lost. So when we work with real numbers, we have to remember that they're being stored as two fixed-length integers. That limits our values in two ways. The size of the exponent limits how big or small our values can be, and overflowing the exponent will result in the special value infinity. The fixed size of the mantissa means that the precision of our numbers is limited, and that can result in rounding errors.